Hey everyone, you know when you look at an X-ray image, that classic black, white, and gray picture of our insides, have you ever really stopped to wonder how it's made? I mean, it seems straightforward, kind of like taking a picture, right? But the reality, well, it's this incredible, complex story that happens in a fraction of a second, on a scale we can't even imagine. It's a story all about energy and matter. It's a microscopic dance between these tiny particles of light, called photons, and the very atoms that make up our bodies. So today, we are going deep into the physics of that dance to really understand the fundamental interactions that make all of medical imaging possible. Okay, let's start with the big picture. When a beam of X-rays hits, say, your arm, it kicks off this whole cascade of events. This chart here lays it all out. It all begins with what we call a primary interaction. That's the physics part, where an X-ray photon literally collides with an electron. This single collision can send that electron flying and scatter the original photon. Then, that high-speed electron zips through your tissue, causing all sorts of havoc, ionization, breaking molecular bonds, which then leads to chemical changes, and ultimately the biological effects that we think of as radiation damage. But for today, we're going to zoom all the way in on that very first crucial step, that primary interaction. What is actually happening in that first trillionth of a second?
So here's the game plan for today. First, we're going to look at the three possible fates that any single X-ray photon can have. Then, we need to set the stage. We'll explore the atomic arena where all this action goes down. After that, we're going to break down the two main events in diagnostic imaging, the photoelectric effect and Compton scatter. We'll put them head-to-head, see how they stack up, and finally, we'll pull it all together to see why this tiny subatomic dance is so incredibly important for every single medical diagnosis that's made with an X-ray.
All right, let's kick things off. I want you to picture a single X-ray photon, just this one tiny packet of energy, and it's hurtling towards a patient. The second it reaches the body, it comes to a fork in the road. It has to choose one of three paths. And believe me, the path it takes changes everything. So here are the three options on the table. First up, transmission. This is the simplest one. The photon just zips straight through the body, doesn't hit a thing, and smacks right into the detector on the other side. Simple. Second is what we call attenuation, or more specifically, absorption. This time, the photon hits an atom and just stops. It vanishes. All of its energy gets dumped right into the tissue. This is what creates a shadow on the X-ray. And third, we've got scatter. Here, the photon interacts with an atom, but instead of being absorbed, it just gets deflected, bouncing off in a totally new direction, losing a little bit of energy along the way. As you're about to see, these three outcomes are the building blocks for absolutely everything in X-ray imaging.
Now, to really get why a photon gets absorbed versus scattered, or just passes right through, we have to shrink our perspective way down. We need to understand the world where these collisions are happening, the world of the atom.
Everything, and I mean everything, the air, the table, our bones, is made of atoms. And they all have the same basic layout. You've got a dense core, the nucleus, packed with positively charged protons. Then, surrounding that, you have this cloud of negatively charged electrons, just whizzing around in their orbits. These are our two main players, the nucleus and those electrons. They're the targets for our incoming X-ray photon. Now, that electron cloud isn't just some chaotic swarm. Nope, it's highly organized. The electrons are arranged in these distinct energy levels, or shells. Think of it like planets orbiting the sun at different fixed distances. We give them letter names, starting from the inside and moving out, the K shell, then the L shell, M shell, you get the idea. And those electrons in the innermost K shell, they're the closest to that positive nucleus, so they feel its pull the strongest. And that pull creates this absolutely critical concept called binding energy. The best way to think of it is like the cover charge to get an electron kicked out of the atom. It's the bare minimum amount of energy a photon needs to have to knock an electron out of its orbit. And because those K-shell electrons are held so tightly by the nucleus, they have the highest binding energy. It's like they're at the bottom of a deep well. You need a much more powerful kick to get them out, compared to an electron that's just floating way out in the M or N shells. Okay, and check this out, because this is where it gets really interesting. That binding energy is totally different depending on the element. Just look at the trend here. Hydrogen, with its one little proton, has a K-shell binding energy of just 0.01 kiloelectron volts, basically nothing. Now, jump down to calcium, a key part of our bones. With an atomic number of 20, its K-shell binding energy is 4.0 keV. That's 400 times higher. Now look at iodine with a binding energy of a whopping 33.2 keV. This is exactly why we use iodine as a contrast agent. Its atoms are way better at grabbing X-rays than our regular tissues. And then you have lead, with 82 protons, a massive 88 keV binding energy. That's why it's so good for shielding. So here's the key takeaway. The more protons you have in the nucleus, the higher the atomic number, or Z, the stronger that pull is, and the higher the binding energy. This rule is fundamental to everything we're about to talk about. All right, with all that atomic groundwork laid, we're ready to meet our first major player. This is the photoelectric effect. And in the story of making an X-ray image, this is our hero. This is the good guy, the interaction that gives us all the useful information. The photoelectric photon is a true all-or-nothing deal. An incoming X-ray photon scores a direct hit on one of those super tightly bound inner shell electrons, usually one in the K shell. Now, for this to happen, the photon has to have an energy that's just a little bit more than the electron's binding energy. And when it hits, bam, the photon doesn't bounce, it's gone. It completely disappears, and it transfers every last bit of its energy to that electron. It is a complete and total absorption. This little diagram walks us through the whole sequence perfectly. So on the left, you see our photon coming in. At point A, it smacks into that red K shell electron. The photon vanishes, and all its energy boots that electron, which we now call a photoelectron, right out of the atom. But that leaves a hole, an empty spot in the K shell. And nature just hates a vacuum. So an electron from a higher shell, the L shell in this case, immediately drops down to fill that hole. And as it falls from a high-energy state to a low-energy one, it has to release that extra energy, which it does as a new, very low-energy photon called a characteristic X. So let's just recap that, because it's important. The whole thing is this neat little cascade. It starts with the photon strike. That leads to total absorption of the photon's energy. That energy is then used to eject the photoelectron. And finally, nature cleans up the mess by filling the hole, releasing a little bit of secondary energy in the process. It's a clean, complete energy transfer, all happening right there at that one atom. So what makes this heroic interaction more likely to happen? Well, it depends heavily on the photon's energy, but maybe not in the way you'd think. I absolutely love this analogy. Picture a ceiling fan spinning. Those are the electrons. And you're throwing a ball at it. That's your X-ray photon. Now think about it. The slower you throw that ball, the more time it spends in the plane of the fan blades, and the better the chance it'll actually hit one. But if you fire that ball like a cannon, it's way more likely to just zip right through the gaps. It's the exact same principle with X-rays. Lower energy photons are actually more likely to be absorbed by the photoelectric effect. As you crank up the photon's energy, the chance of this happening drops like a rock. But of course, not every interaction is that clean, all-or-nothing absorption. It's time to meet the second major player in this story, Compton scatter. And if the photoelectric effect is our hero creating beautiful contrast, well, Compton scatter is the villain, creating noise and fog that just messes up the picture. Okay, so unlike the photoelectric effect, which targets those tightly bound inner electrons, Compton scatter happens when a photon hits a loosely bound outer shell electron. These guys are so far from the nucleus that their binding energy is pretty much zero. They're basically free agents. So in this interaction, the photon doesn't give up all its energy. Now, it just gives a portion of its energy to the electron, knocking it out of orbit. And then the original photon, which now has less energy, ricochets off in a completely new direction. Honestly, the best way to get your head around Compton scatter is to just think about a game of pool or billiards. The incoming photon? That's your cue ball. The outer shell electron? That's the object ball. And what happens next is just straight up physics, conservation of energy and momentum. It all depends on how they collide. So let's look at one possibility. Imagine the cue ball, our photon, just grazes the object ball. It's a glancing blow. As you can see here, the photon gets deflected, but it keeps almost all of its original energy. In this case, like 98% of it. The electron gets a tiny little nudge, but not much. Very little energy gets transferred. This is what we call a small angle scatter event. The angle that the photon scatters at tells you everything. The bigger the scatter angle, the more energy was transferred to the electron. A 90-degree scatter, where the photon just veers off to the side, is a much more direct hit than that little glancing blow. It means a pretty significant chunk of energy was transferred to the electron, and the scattered photon carries on with a lot less energy than it started with. And here's the other extreme, a direct head-on collision. The photon hits the electron dead on. The electron goes flying straight forward, and the photon scatters straight backward, a full 180 degrees. We call this backscatter. This is the absolute maximum amount of energy you can transfer in a Compton interaction. The photon gives up as much energy as it possibly can and retreats, while the electron just rockets forward with all that new kinetic energy. So now we have our two main characters on the stage, the photoelectric effect, which is that clean absorption, and Compton scatter, the messy billiard ball collision. To really see how they shape an X-ray image, we've got to put them side by side, head to head, and compare what makes them tick. This table just lays out the critical differences beautifully. Let's walk through it. Photon fate. Photoelectric, absorbed. Compton, scattered. Easy enough? Electron involved? Photoelectric targets the tightly bound inner shell guys. Compton goes for the loosely bound outer shell ones. Now for the big one. Does it depend on the atomic number Z? For the photoelectric effect? Oh yeah, big time. It's proportional to Z to the third power. That is a massive dependence. It's why bone with a higher Z absorbs so many photons. Compton scatter? Doesn't care about Z at all. It happens just about equally in bone and in soft tissue. And photon energy? Photoelectric hates high energy. Its probability plummets. Compton also decreases with energy, but way, way more slowly. And all of this leads to the bottom line, the impact on the image. Photoelectric effect creates contrast. Compton scatter creates noise and fog. And this chart really shows you how this battle plays out. At lower X-ray energies, especially in something with a high Z number like bone, the photoelectric effect, our hero, is totally dominant. It's not even a contest. But as we crank up the energy, its probability just nosedives. In soft tissue, at around 30 kV, the chances of either one happening are about 50-50. And then, as we keep increasing the energy into the range we use for a lot of exams, Compton scatter, our villain, takes over and becomes the most likely thing to happen by far. So let's bring this all home. We've been deep in the weeds talking about atomic shells and cosmic billiards. Now, let's connect this whole microscopic dance directly to that image a doctor is looking at to make a life or death decision. Here it is, the whole story in a nutshell. The photoelectric effect is the hero. Because it's so insanely dependent on that Z number, it happens way more in bone than in soft tissue. More photons get absorbed in bone, which means fewer photons hit the detector behind it, and that's why bone looks bright white. That difference in absorption is what creates the image. It's where all the useful contrast comes from. Compton scatter, on the other hand, is the villain. Those scattered photons, they still hit the detector, but they're coming in from all sorts of random directions. They carry zero useful information about where they came from. They just add this uniform layer of grayness, like a fog, that washes out all that beautiful contrast our hero worked so hard to create. And this, right here, is the central puzzle for every single person who takes an X-ray. We know that using a higher energy beam can let more photons get through the patient, which is good for reducing the radiation dose, but we also know that as we crank up that energy, we're killing off our good photoelectric interactions, and we're increasing the amount of bad Compton scatter, which just ruins the image quality. So the final question is, how do they find that perfect sweet spot? How do they pick an energy that's just high enough to get through, but low enough to maximize that heroic contrast and create a crystal clear diagnostic image? Well, that balancing act, that is the art and science of radiology, and it's all built on the foundation of this incredible, invisible dance of photons.